Hey, welcome. This is Calculus 2, and we're starting way back in 5.7 with the natural log rule for integration. Okay, so what is the rule? Basically, we get it from what we know about the derivative of the natural log. So the derivative of the natural log of x, you probably learned in Calc 1, is equal to 1 over x. But not only that, we could also say that the derivative with respect to x of the ln of the absolute value of x is equal to 1 over x. So considering the integral is just the reverse of a derivative, it goes to reason that the integral of 1 over x then dx is going to be the natural log of the absolute value of x plus c. Okay? Be aware that we can always rewrite this integral in different ways. You could write it as dx over x. You could write it with a negative exponent, x to the negative 1 dx. Okay, so just be careful. So let's look at, I guess, example 1 in the book. And we have the integral of 2 over x dx. So with integrals, the first thing you generally will want to do is factor out any constants. So there's a factor of 2 we could pull out of the integral, and then you're left with 1 over x dx, which is the natural log. Okay, so you got 2 ln absolute value of x plus c. Okay. The book goes on to say you could use the power rule there. So you have the ln of basically the absolute value of x squared plus c. Anything squared is going to be positive, so you need not have to use the absolute values if you don't want. You just write it ln of x squared. But this first answer, honestly, is just fine by me. Okay. Let's look at another one. So probably here with now a u-sub. So find the integral of 1 all over 4x minus 1 dx. So with my u-subs, what I like to do is first state the u-sub. So u in this case is going to make the denominator 4x minus 1. And then I like to find the derivative and the differential form. So instead of writing du over dx, you just put the dx on the other side. So du will equal the derivative of 4x minus 1. The derivative of 4x is 4. Derivative minus 1 is 0. And then we're going to slap in that dx. Then I like to solve for the dx. I don't think the book is doing that. No, they're not. They're doing something kind of weird. So the way I do it is divide both sides by 4. And you have dx equals du over 4. Okay. Then I'll do my substitutions. So I have 1 all over u, and then I'm going to replace, so 1 over u is from this first part, and then I'm going to replace the dx with du over 4. We'll get the same results as what they do. I think the way they do it is a little bit unintuitive, So, yeah. Okay, so my next step, I'm going to factor out the constant part, the 1/4. So I get 1/4 here. Then I have the integral of 1 over u du, which is our natural log integral. So you get 1/4 ln absolute value of u plus c. And then I'm going to back sub. Okay. It's no big deal. You could, of course, use integrals to find area bounded by curves. So example 3 here, they want us to find the area bounded by this graph of y equals x over x squared plus 1, the x-axis, and the line x equals 3. So if we graph this guy, x equals 3 is 1, 2, 3 out here. And then the graph of x over x squared, the x-axis I have no idea. We can go to Desmos and see what the heck the thing is. Desmos. Okay, so something like this. And then at 3, I'm not sure what it's doing, but it's going to go something like that. Okay, so the region we're after then is going to be this region. And so on our integral, we can just integrate from 0 to 3 of this function x over x squared plus 1. And that integral then will give us the area underneath that curve. Okay. Okay, so let's do a U sub again. So it looks like usually in this section, your best bet is just to let the denominator be U. So here we go. U is x squared plus 1, and then du is going to be 2x dx. And again, I like to solve for dx and do my substitutions. I think it's easier than what the book is doing. So du over 2x. I'm going to drop the limits on the integral because technically when you do your U sub, it changes the limits on the integrals. You could do a change of limits. Some people like to do that, but I just like to put them back in at the end. Okay? Okay, so here we go. Got x all over my u times dx, which I just found to be du over 2x. The x's will cancel out. Boom, boom. And you can factor out a constant of 1/2. So you get 1/2 integral of du over u. And of course, that's your natural log integral. So ln absolute value of u. This is a definite integral, so I have to remind myself to evaluate. Oops, and I can't put the limits in just yet because I'm still in terms of u. I would have to change them if I put them in right there. So I got 1/2 ln absolute value back subbing x squared plus 1, and now I can put my limits back in. Okay, so here we go. 1/2 ln, evaluating the antiderivative first at 3. So 3 squared is 9 plus 1 is 10. And then minus 1/2 ln, 0 squared is 0 plus 1 is 1. And ln of 1 is just 0. So you're just going to end up with 1/2 ln, absolute value of 10 is 10, so 1/2 ln of 10. Yeah, and then they got a nice little approximation for us. And here's a picture. I was looking for the picture earlier. There it is. Okay, sometimes it's not all that easy to recognize the quotient forms, but usually, if you have some sort of ratio, letting the denominator be your U sub is the way to go. So let's look at least part A here. You have the integral of 3x squared plus 1. This is example 4 all over, let's see. Sorry, just one second. Actually, I want to pick one of the problems from my notes. Okay, so. And this is going to be the first video quiz. So in every video, I'm going to embed like a mystery problem. And when you watch the video, you have to basically write the mystery problem down, and then you're going to take a picture of it or scan it and upload it to your computer. And you're going to compile them all into a PDF and send them to me periodically. That way I'll know you're watching the videos. I think I call them video quizzes, but they're not really quizzes. You just basically copy down the problem like I copied it. So this is the first video quiz and here for section 5.7. So you'll probably turn in 5.7, 5.8, 5.9, and 6.1, those video quizzes for your first set. Okay. Okay, so this is the first video quiz, and it's very similar to example 4 there, part A. But anyways, we have x squared minus 2x all over x cubed minus 3x squared dx. Okay. And this kind of looks like a lost cause with regards to the U sub, but it'll work if you just let the denominator be your U sub. So we have x cubed minus 3x squared, and then du, the derivative of that, is 3x squared minus 6x, and then dx. And you're probably worried, is there going to be a nice cancellation? Because for these subs to work, the U sub to work, all the x stuff has to go away, right? You can't have a mix of variables. So anyway, solving for dx, you get du all over, and I'm going to factor that, and then you'll see, oh, that's going to be a nice cancellation. So if you factor out the 3, you'll have 3 times the binomial x squared minus 2x, and that's going to give you a nice cancellation. Okay, so let's go ahead and rewrite it. I have x squared minus 2x all over u times dx, which is now du all over 3 times x squared minus 2x. And you see the nice cancellation, got rid of all the x material. There's a constant floating around, so you have to always pull out your constants. So here I have 1/3. That's my constant. And then I have du over u left over. Integrate that, so that's just our natural log of u plus c. And then finally back sub. So 1/3 ln absolute value x cubed minus 3x squared plus c. Okay. Let's see what else they got for us. Long division problems. So you're going to have to remember how to do long division to get some of these problems done. So we have x squared plus x plus 1 all over x squared plus 1 dx. Okay, so if you have the same degree in the numerator and denominator, you do long division. There's other tricks you can do. If the degree of the numerator is higher than the degree of the denominator, you definitely do long division. Anyways, let's go ahead and do our long division. So we want to divide x squared plus x plus 1 by x squared plus 1. You could use placeholders if that's what you learn how to do. That's usually what I teach in pre-calculus. So x squared plus 0x plus 1. And then how many times does x squared go into? So what times x squared equals x squared? 1, right? So 1 times x squared is x squared, 1 times 0x is 0x, and 1 times 1 is 1. And then you subtract these guys, and x squared minus x squared is 0, x minus 0x is x, and then 1 minus 1 is 0. And that's pretty much all you have to do for this one. Rewriting it then always takes this kind of clockwise rotation. It'll be 1 plus this thing all over this thing. So then I could rewrite my integral as 1 plus x all over x squared plus 1. And then dx. Okay. Then you could integrate by integrating the integral of the sum is equal to the sum of the integrals. So the first, you have integral of 1 dx plus the integral of x over x squared plus 1 dx. Integral of 1 is just x. And then on that second guy, it looks like you're going to need another u sub, right? So I'm going to go u into is x squared plus 1. And they do some weird thing where they kind of multiply in a factor. So what my u sub is doing is kind of producing that 1/2 factor that pops out in front. But anyways, du is 2x dx, and then dx is going to be du all over 2x. And so my integral will become x all over u times du all over 2x. And then I have x plus, factor out the constant, 1/2. The x's will cancel. So I get plus 1/2 integral du over u. So that will be x plus 1/2 ln absolute value of u plus c. And then finally x plus 1/2 ln absolute value of x squared plus 1 plus your integration constant. Okay. What the heck is this thing? Oh, this is one of the weird ones. So example 6. So usually with my u subs, I do my u, I get my differential, and then I do my substitutions. But sometimes the substitution won't clear everything out. So you have to turn around and solve for one of the variables. So let me show you what I mean. I'm going to let u equal x plus 1 in this case. Okay. And then, of course, my du will just be dx. Derivative of x is 1, the derivative of 1 is 0. And then if you did this sub, it wouldn't get rid of the x in the numerator, right? You wouldn't have that nice cancellation like we see in the previous problem. So what you do is kind of just borrow this equation and solve it for x, okay? So I'd have x equals u minus 1, and then that'll allow me to get rid of all the x terms when I do my substitutions. So I'll have the integral of 2 times x, which is now u minus 1, all over u squared times just du. Dx is du. Okay. All right. I'm going to go ahead and distribute the 2. And then I'm going to kind of what they call butterflying, or you might call it filleting. So if you have a sum over a single term and a fraction, you could split it up this way. You can't do the upside down version of it, right? But you could do it when it's in this form. So I'd have the integral of 2u over u squared is the same as 2 over u. And then minus 2 over u squared, I'm going to rewrite it as 2u to the negative 2. That will make it easier for me to do my power rule on my integral. Okay. Okay. So the first integral will be 2 ln u, and then minus 2 u to the negative 2 plus 1 is negative 1, and then I'm going to divide by that new exponent, negative 1. Clean it up a little before I back sub, and this should be absolute value of u. It'll be negative, negative, so plus u to the negative 1 is 1 over u, so plus 2 over u plus c. And then finally, go ahead and back sub. So ln absolute value x plus 1 plus 2 all over x plus 1 plus c. Okay. Right, so this one, example 7, a little bit more complicated. And you have the integral of 1 all over x ln x dx. And, you know, you could try to do a u sub for that entire denominator, but you're going to end up in a world of hurt because you'd have to do the product rule, and you'd end up with 2 terms, and there's no way it would cancel. But look, here is kind of a function, and here is its derivative, okay? So if you can find that relationship between a function and then you're looking around, you see its derivative floating about, usually that means you do the u sub on that particular function. And then once you do the u sub, you'll have a cancellation with its derivative if it's already inside the integral. A lot of it just comes down, in my opinion, to experience doing integral after integral after integral. So there's really, in my opinion, no magic way. They'll say that integration is more of an art, and taking derivatives is more of a science. I don't know if you agree with that, but some people think that way. Okay, so anyways, I'm going to let my u equal ln x, and then my du equal 1 over x dx. And then you could solve for dx, and you'll get your x du. Okay. Then I'm going to do my substitution. So I have the integral of 1 all over x times u times dx, which is x du. And you see there's that nice cancellation. You get rid of the x's. You'll have the integral of 1 over u du. And then, of course, that's the ln of the absolute value of u plus c. And then you can back sub. Looks a little weird. ln of x plus c. Okay, little unusual answer. Yeah, and you know, we ultimately would like to be able to integrate pretty much anything that can come our way. We can integrate pretty much any polynomial, and now we can almost integrate almost any rational function, right? Because rationals are just ratios of polynomials. And then you start thinking, what is the possible universe of functions that we know of, you know? And what do all their integrals look like? What are all the the derivatives look like. Studying that kind of stuff is what they call studying a differential field. And it works a little bit like just studying your addition in the number system and the integers and stuff like that. It's an algebra, a type of algebra. So if you take a class called abstract algebra, a lot of teachers have to take that. It's kind of related to that. So you have rings and groups and fields and stuff like that. Okay. Anyways, let's see what else they got for us. Oh yeah, so not only can we attack pretty much every polynomial and then pretty much every rational function, we can integrate those. Now we're going to be able to integrate pretty much any trigonometric function as well. So example 8, we're going after the integral of tangent. Okay. Now let's just look at the homework. The integral of cotan is going to be very similar. But the trick is to rewrite it as trigonometric identity using here I guess, I forget what they call this, is the quotient rule. But anyways, we learned that tan is sine over cosine, and then we could use a u sub on cosine to get our answer. So du would be negative sine x dx, and then dx is going to be negative du all over sine x. And then we can do our subs. So we have the integral of sine x over u times negative du over sine x. Thankfully, the sine x's, boom, boom, they're gone. You can factor out a negative, and you get du all over u. And so that's negative ln absolute value of u plus c, which is then equal to negative ln absolute value of cosine of x plus c. Sometimes you don't see that form. In some books, what they do is use the log rule to take this negative and put it in as exponent on the cosine. And then you would have ln of the absolute value of cosine of x to the negative first power. And of course, you could rewrite that as 1 over cosine. And then you could rewrite that as just secant. Okay. So you'll see either form. You'll see me write either form. Either form is correct. So that is correct. And this guy right here is also correct, just in case you're wondering. Yeah, and they do that weird thing with the negative. Okay, great. The secant formula is a little bit more complicated. It's not intuitive. Like if you fold around enough, you could probably figure out the integral of tangent. But the integral of secant x, in order for that to become like a nice ln doing a u sub, you're going to have to be a little bit more creative. And the trick is to multiply, so pretend secant is secant over 1, and then multiply top and bottom of that by secant plus tan. Right? Then you could do a u sub on the denominator. Let's first distribute this. So secant squared x plus secant x tan x all over the secant x plus tan x. And you see the function in the denominator, the secant x plus tan x, its derivative is sitting in the numerator. Okay, so you're going to go let u be secant x plus tan x, and then du, the derivative of secant is secant x tan x. The derivative of tan is secant squared x, dx. And then you could solve out for dx as du all over secant x tan x plus secant squared x. Okay. Just go ahead and do your sub then. So this would be the integral of secant squared x. It's a lot of writing. I think that's why the book does their doesn't really do the u subs like me. It's because when you do it like me, you have a lot more writing. But I still am a firm believer in doing a u sub the way I do it. X then times du all over secant x tan x. What is it? Sorry, secant x tan x plus secant squared x. And then there's that nice cancellation, boom, boom. That stuff in the denominator should just be u at this point. And of course that will turn into the integral of du over u, which will be the ln of the absolute value of u, c, which will then equal the ln of the absolute value of secant x plus tan x. The cosecant version is pretty similar as well. Same sort of trick. The book goes ahead and gives you all the six basic trigonometric formulas. You should have these. You should be able to get the first four with no problem. Usually on a test, I won't harass you with the integral of secant or cosecant. But usually, if you could do those integrals, it'll help you. The more familiar you are with it, the less time you have to spend looking it up. So just keep that in mind. Anyways, sure. Let's look at example 10. So we have the integral from 0 to the pi over 4 of the square root of 1 plus tan squared x. So I expect you to kind of be familiar with trig identities, especially the what they call the Pythagorean identities. So sine squared plus cosine squared is equal to 1. If you divide everything by cosine squared, you get tan squared x plus 1 equals secant squared x. If you divide everything by sine squared, you get 1 plus cotan squared x equals cosecant squared x. So the second identity allows you to do a u-sub here, or not a u-sub, but just a normal sub, right? So you could plop secant squared in the place of 1 plus tan squared. Okay, so we've got secant squared here. And then the square root of secant squared, you could just write as secant. And then from above, we know that's equal to the ln of secant x plus tan x. And then evaluate from 0 to the pi over 4. Okay, so that would equal ln of the absolute value. Secant of pi over 4 is root 2. Tan of pi over 4 is 1. And then minus ln of absolute value of 1 plus 0. Ln of 1 plus 0 is just 0. Ln of 1 is 0. So it looks like you're just getting ln of, and you don't need the absolute values because root 2 plus 1 is positive. So ln of root 2 plus 1. We did talk a little bit about average values. I don't think that's going to be a big part of what we're going to be doing, so I'm going to skip that. And then it just goes to the exercises. Okay, so I think we should be okay with the exercises. Maybe look at one. That one looks annoying. Let's try this number 7, this cotan version. Integral of cotan of theta over 3 d theta. Okay, so I'm going to rewrite it as what? Cosine of theta over 3 all over sine of theta all over 3 d theta. Then I'm going to do u sub for sine. Okay, so du, the differential there is cosine of theta over 3. Then you got to do a chain rule. So the derivative of theta over 3 is 1/3, and then d theta. And then solve for your d theta. So dividing both sides by cosine of theta over 3 is going to give you 3 du all over cosine of theta over 3. And then we could do our subs. Okay, so the integral of cosine of theta over 3 all over u times 3 all over cosine of theta over 3 d theta. Nice cancellation. And with factor out 3, so you get 3 integral. This should be a du now, not d theta. You end up with the 3 times the integral of du over u, which of course is ln. So 3 ln absolute value of u plus c, and then you want to back sub. So we get 3 ln absolute value sine of theta over 3 plus c. And then we should be able to type that guy in without too much problem. 3 ln sine of, need a Greek symbol for theta, theta divided by 3. I need absolute values here as well. So absolute value and then plus c. Let's see if it works. Oh, ruh-roh. What did I do wrong? You gotta put a capital C in there. That is lame. Alright. Whatever. Anything else? I think we'll be okay. This is just finding area. Find area. Okay. So we'll leave it at that, and thanks for watching, and we'll see you next time.